What is DIP? DIP stands for Dependency Inversion Principle, and it is one of the most solid principles in object-oriented programming. It is formulated by Robert C. Martin, and according to him, high-level modules should not depend on low-level modules. Both should depend on abstractions. Abstractions should not depend on details. Details should depend on abstractions. In simpler terms, this principle suggests that software design should be based on abstractions, not concrete implementations. This promotes loose coupling between components, making the system more flexible, maintainable, and easier to modify or extend. For example, rather than having a high-level module directly depend on a specific low-level module, the higher-level module should depend on an abstract interface that low-level module implements. This allows for swapping out different implementations of the low-level module without needing to modify the high-level module as long as they adhere to the same interface. Next is the purpose of DIP. First one is decoupling. DIP aims to reduce the direct dependencies between higher-level and lower-level components in a system. By introducing abstraction layers and interfaces, it allows components to interact through well-defined contracts rather than directly depending on concrete implementations. Next is maintainability. Since no matter what modification you will do in a low-level module, it doesn't affect the high-level module or the components of your system, which means that the code is easier to maintain. Then lastly is flexibility. DIP promotes flexibility by enabling components to be easily replaced or extended without affecting other parts of the system. By depending on abstractions rather than concrete implementations, it becomes possible to swap out implementation for another without requiring changes to higher components. This is an example of an online store application. This code does not adhere to dependency inversion principle because it directly depends on concrete implementations of payment processors, which are the PayPal and Stripe, within the checkout method, leading to tight coupling. The next, payment processor implementation. The payment processing logic is directly implemented within the checkout method of the store class, based on the provided payment processor string. So this code directly processes payments based on provided strings, leading to tight coupling and less flexibility. Let's try to apply dependency inversion principle. Now, the code adheres to the DIP by introducing an abstract payment processor interface and depending on it in the checkout method of the store class. This allows for loose coupling and flexibility in providing different payment processor implementations. The payment processor implementations, which are PayPal payment processors and Stripe payment processor, are separated classes that implement the payment processor interface. The checkout method of the store class interacts with these implementations through abstraction. The code defines abstract payment processor interface and implements specific payment processors using this interface. This promotes loose coupling and allows for easy substitution of payment processor implementations. By adhering to the dependency inversion principle, there is always abstraction interfaces, and it promotes loose coupling between components, leading to a more flexible and maintainable code base.
Without applying the dependency inversion principle, we created two classes with main method. The first class is high-level module, and the second class is the low-level module. Here, in the high-level module, we create an instance variable low-level module of a type low-level module. In the constructor, it initializes the low-level module by creating a new instance of low-level module. We define also a method perform operation, which calls the do something method of low-level module. Under the low-level module class, we define a method do something which simply prints low-level operation perform. And the main class, in the main method, which creates an instance of high-level module and calls the perform operation method of high-level module. By applying the dependency inversion principle in the high-level module, we define an instant variable of module of type iModule. In the constructor, it takes an argument of iModule and assign it to module. And we define also a method perform operation which calls the do something method of module. Under the low-level module class, here we implements the iModule interface and implement the do something method required by the interface, which prints the low-level operation perform. And the interface iModule, we declare a method do something which must be implemented by classes that implement this interface. And the last, the main method, we created an instance of low-level module, passes this instance as an argument while creating an instance of high-level module, and calls the perform operation method of high-level module. Here, just one. The high-level module directly depends on low-level module, making it tightly coupled to the concrete implementation, while the second approach, high-level module, depends on an abstraction, iModule, and low-level module implement this abstraction. This reduces coupling, making the code more flexible and easier to maintain, as high-level module is no longer dependent on the specific implementation of high module. Dependency, the inversion principle, promoting loose coupling and high cohesion, which are desirable characteristics of software design.
Next example is Python. As you can see here, in this code, it does not adhere the dependency inversion principle, while this code adheres the dependency inversion principles. Let us know the difference between this one and this one. Here, the user manager does not require a logger to be passed during initialization. Instead, you have to explicitly set the logger using the setLogger method, which is here, before calling the registered method. This violates the dependency inversion principle because user manager now depends on the concrete implementation, which are the file logger and the console logger, rather than the abstraction logger. In this code, adheres the dependency inversion principle. As we can see, a file logger or instance of file logger is created and passed to an instance of user manager. And when the register is called on this user manager instance with a username, it logs a message indicating that the user registered successfully. And this message is appended to the file log.txt. Similarly, an instance of console logger is created and passed to another user manager instance. And when the register is called with on this user manager instance with a username, it logs a message indicating that the user is registered successfully. And this message is printed to the console. This code allows for flexibility in logging, as you can easily switch between logging to a file or logging to console, or even implement new types of loggers by subclassing logger. And providing custom implementations for the log method. Here, the file logger and the console logger is the low-level modules, while the user manager is the high-level modules, and the logger is the abstraction. In the dependency inversion principle, the high-level modules and low-level modules should not depend on each other. Instead, they will depend on the abstraction, which is the logger. The high-level modules define the overall logic or the interface, while the low-level module is in the specific implementation.